Hi everyone. This is a very short demonstration of how to use a virtual lab for thin converging lens. So when you click on the link I provide in my Canvas page, you are going to be referred to this virtual lab. What is what over here, guys? First, you can see the lens. It's a thin lens, right? And it's converging lens. It looks like it's kind of bumped on this side and bumped on this side. What else do we see over here, guys? We see the object, and it's actually marked that it's object, but it's hard to see on this, like maybe kind of all the numbers that's its object. You can move the object if you pull it, like, or kind of click on this red square, you can move it, and you see object is written. You see what is changing, the distance to the object. Here the distance is negative because we are sitting on negative side of the x-axis. You can move your object over here as well. Okay, what else can you move over here, guys? Well, you see over here is f. F is the focal distance of the lens. Everything on this lab is measured in millimeters. I want you to convert everything in centimeters. You also can change focal distance. I'm changing focal distance to 10 centimeters or 100 millimeters. So here is my object, and what is over here is my image. How do we get this image? You see that they actually write down on the top of the image that it's image. You cannot move the image. Object you can move. You see the controls. The red square and the green square are controlling the image. Red square controls position of the image. Green square controls the height of the image. You can make the object, sorry. You can make object higher, like, or like smaller or bigger. Image is already obtained using the lens, and you cannot control it unless you move the object. Okay, so what they write around the image, that it's a real image, means that the light actually intersects at this point. Inverted, while you see it's upside down, right? Magnify, while you see it's a little bit bigger than actually my object. I'm going to make object smaller so you see the difference. It's like maybe 1.5 times bigger, right? Well, I'm going to move a little bit. No, I'm going to show you how the light goes from the object to the image. Here you can click and show like two rays. I think that's going to be the best. So how do we build image using geometrical optics? First, we remember that for converging lens, parallel light goes through the lens and goes after that through the focus and converges at focus, and we can kind of draw the parallel line parallel to the axis of the lens up to the lens, and then bend it through the focus, and that's a green light, right? Goes this direction. Light which goes through the center of the lens just does not know that there is a lens. It's not bent, and it's just a straight line. So you connect the point on your arrow through the center of the lens and just continue a straight line. Eventually, these two lines are going to intersect, and this intersection point is going to make actually the arrowhead of my black arrow, and that's where the image is going to be located. And when I move my object, you are going to see that image is going to move too. Let's watch how it's going to kind of move. You see, I'm making my object closer to the focus, and you see how big is image becoming. Okay, so now, if I move it too close to the object, too close to the lens, eventually it's going to disappear, right? But not forever. If you look at this green and red rays, you are going to see that they, from converging, becoming diverging, going parallel, but a little bit away from each other, right? This, if you can look at continuation of these two lines, you're going to see dashed lines. And eventually, guys, if you are close enough to the lens, you are going to get image on the same side of the lens. Just this image, you see the image is made out of dashed lines, or like something like not real. Actually, they are going to call it virtual image. Virtual image does not exist in nature. Actually, if you look from this side on the picture, what you are going to see, you are going to see the ray which goes away from the red one. The green one goes away from the red one. Your brain is going to kind of continue this rays and intersect them somewhere over here and create virtual image. So in nature, there is nothing. So light does not intersect here. But in your brain, there is going to be image of arrow. And that's how magnifying glass is working. When you look at some small letters through the magnifying glass is creating them bigger and further away from the lens. That's how they're not really bigger, right? They're same big, but magnifying glass is making them look bigger because it diverges a little bit the light from actual small letters and makes them bigger. Okay, you don't need to do this experiment. You don't need to bring it that close. So do not overpass the focal point. So stay well, between 10 centimeters. Maybe you can go over 20, 25 centimeters. I'm asking you to do two measurements. So I'm asking you to put, for example, your arrow somewhere here and collect distance to the object. And usually it's written under U letter. I don't know why do they denote it as U, but for us, it doesn't matter, right? You just call it P. And collect this distance. Very strangely, but well, they do not write the distance over here next to the arrow. They put it over here. You collect the number from over here. By the way, they put meters over here. I think they did a little mistake, and that's millimeters. So please do not think that it's meters. It's millimeters, and also millimeters here. Now, guys, the height, it's 55 millimeters, the height of arrow here. And you see this arrow is smaller, and it does at 36 millimeters here. Again, all these meters are actually millimeters. Well, what you can do to play a little bit with this program, you can choose a different object. For example, like just a star over here, and that's going to be image of the star over here. And you can move it, and you see that closer to the focal point you get, bigger is going to become your image. Farther away you get, smaller is going to become. Eventually, that's going to be tiny, right? You get far away from the two focal distances. One focal distance is 10 centimeters, 20 centimeters, 30 centimeters, even 40 centimeters. Your image is very small, right? Okay, you can play a little bit with this program. Here you can change modes a little bit. If you don't like what you did, you changes you did, you can just click reset. It also has several short movies which you can watch how everything is moving. You can just go down here and look at scenario 1, scenario 2, and scenario 3, 4, and divergent lens. You even can look at divergent lens. Okay, what else you can do? You can change the object you have. You have arrow, you can have pencil, and you can have smiley, and you can have star. I'm asking you to do two measurements. So put your object somewhere like between 10 centimeters and 20 centimeters, maybe like 25 centimeters. Do one measurement of P and Q and record the height of the object and the height of the image, and then move position and bring it closer, and also record like, well, don't bring it that far away so you don't see the image, but kind of record a different position. You can change the size, but bigger size over here is going to create bigger size over here. You probably are not going to see the whole object. If you create object too big, image is not going to be like fitting in your screen, but doesn't matter. Actually, this yellow window is still going to show you the height. Okay, what else you can change over here? Well, instead of 2 rays, you can see 3 rays. I'm going to explain you what the third ray is doing, but I'll need to move this one, the object, a little bit farther away. What is the third ray? Again, let me start. The first ray is parallel to the axis, bends in the lens through the focal point. That's how we build it. A second ray, we go directly through the center of the lens and don't change it. Just don't bend it, just a straight line. Intersection is going to give you position of the image. If you wish, you can do a third ray. It's not necessary because it's going to intersect at the very same point with 2 others. But the third ray goes through the focal point. Imagine that you kind of have a source which sits right at the focal point. Then the light goes from it in all directions. Then if you put source in focal point, the light which goes from the lens is going to be parallel. It's kind of opposite, right? You have parallel light, it is collected in the focal point. You have light which goes from the focal point, it's going to become parallel light. And that's what is going to happen. It's going to intersect the lens and become a parallel line to the axis. And it's going to intersect at the same point. But I don't know, if you like to kind of see 3 rays, that's up to you. But I think 2 rays is enough. They also have many rays. Well, many rays is not very good, actually. They show like lots of different rays. And I really don't kind of see like like how it's useful to have like all these many rays. I actually suggest you guys to see just 2 rays. It's going to be enough. Please look how this diagram is built. In the quiz, I'm going to ask you to build a similar diagram, okay? I don't think that you need anything else from here. So basically, we are collecting from here. We are doing 2 measurements and we are collecting P, distance from lens to the object, which is sitting over here, Q, which is distance from image to the lens and sits over here in the yellow box, height of the object above the object, height of the image here in the yellow box. You collect all these 4 numbers and then move your objects a little bit away. You can change the height also if you wish, like make it smaller or bigger. It's not going to change like a result of your experiment. And then collect again height, P, position of the object, and the height of the image and position of the image. Put everything in a table, do calculations, and answer my questions. That's all for this lab, and I'm hoping that you will like it. And thank you, University of Singapore, for making up a nice demonstration for us.